Hello and welcome to Luckymath. In my earlier videos I was talking a lot about matrices. I told you how to add them, I told you how to multiply them, but what I didn't tell you is why do we need them? And in this video I'm gonna show you why we need matrices. So for this I'm gonna need two coordinate systems. Let this be the R2 for convenience, with an origin, a y-axis, an x-axis. Let this again be the R2. And let's choose some random vector up here. And let this be the vector 2, 1. So this is the vector with x-axis 2 and the y-coordinate 1. And what I want to tell you first is that all the vectors which live in this coordinate space, they all start at the origin. So in a coordinate space, there are only position vectors. Maybe you have learned that this vector is exactly the same as this one, so it wouldn't matter where you start with your vector. As long as it has the same direction and the same magnitude, it would be the same vector. But this is true for affine spaces where you don't choose your origin specifically, but here we have chosen our origin, and so all the vectors that we are working with or that exist in this space, they all start at the origin and are therefore position vectors. So our aim now is to transform this vector up here to a new vector, and the new vector, oops, this should be R2 as well. The new vector should be this one, and let this be the vector with a y-coordinate 2 and x-coordinate 4, so this would be the vector 4, 2. And now I ask you, what would you have to do in order to get from 2, 1 to your new vector, which would be 4, 2? So what would you have to apply to this vector in order to get to your new vector? And this is obviously very simple, because you see that this new vector, or the resulting vector, is exactly twice the argument or the original vector. So all we have to do is to multiply times 2. So this was really simple, and you might ask, why are we doing this? So let's try and write down a function or a map or a transformation that takes each vector xy up here and transforms it such that we get the twice the vector, or basically we stretch it by the factor 2. So our map f would go from our domain R2, so that's where the argument lives in, to our codomain R2, that's where our resulting vector lives in. Note that these are the same vector space as R2, but still you need to differ between the two spaces, because this upper space is where the argument lives in, so the domain, and this space is the codomain where the resulting vectors live in. So therefore I drew two coordinate systems to really differ between the two spaces. Then we have an argument which lives in the R2. If we choose a random argument, this is simply with coordinates x, y, and this would then get mapped to twice the argument. Really simple, right? So what I want to tell you is that as long as your map stretches your vector on this same line that the vector already is, so in the same direction, so you could multiply the vector by by 2 to get this vector, or by 2.5 to get this one, or you can also shrink it by 1/2, you get this one, or mirror it to the other side. So all these operations, what you do is you multiply by some scalar. So we could say that this family of functions which stretches or shrinks your vector, we could denote it by f lambda. So this is some family of functions, and let's now replace this 2 by a lambda to specify that these are all the functions which stretch or shrink your vector, where of course lambda is just some real value. So far so good. This was really simple, and you still wonder why we need matrices. So let's get to the second example. So we again need 2 coordinate systems. So let this be again the R2 for convenience, with a y-axis, an x-axis, and an origin, and let's have another coordinate system. And in this case we choose again a random vector up here. In this case we want the vector, let's say 1, 3. To make this a bit more interesting, instead of choosing 2, we chose a 3. Amazing. So what we want to do is now let's try and mirror this vector at the x-axis to get a new vector, which would be this one. So it has an x-coordinate 3 and now a y-coordinate -1. So this vector up here is obviously the vector 3, 1. And what we want is the new vector, so to transform this upper vector to your new resulting vector 3, -1. So I ask you again, what would you have to apply to the vector 3, 1 in order to get your resulting vector 3, -1? So what would you have to do? What would you have to apply? And you might say, well, let's try and multiply by some scalar as we did up here. So maybe let's try and multiply times -1. But then you already see we get -3 up here, which it shouldn't be. And you obviously see that also this operation doesn't stretch or shrink your vector in the same line. So this obviously is not a possible operation. Now maybe you have the idea to, let's say, add some vector. Maybe let's add 0, -2. And then we get the right answer, right? However, this solution is only a solution for the vector 3, 1. So this operation would only mirror the vector 3, 1, but it wouldn't mirror, for example, the vector 5, 4 or any other vector. So this operation only works for the vector 3, 1. What we want is an operation that mirrors all possible vectors in the R2 to a new vector in the R2. So what we need is something else. And the solution is matrices. Exactly. So what is the matrix that we need in order to get this result? So the matrix we're going to apply to this vector, and applying always means matrix multiplication. So we apply a matrix to a vector. This means you matrix multiply the two objects. So in this case, I just tell you the solution. We need a 1 up here, a 0 here, another 0 here, and a -1 here. And yes, it's true, there would be other examples or other matrices that mirror this vector to this vector. However, this is the only matrix that mirrors all the vectors at the x-axis. All right? So what you have to do is you matrix multiply, let's just abbreviate this by MM. You have to matrix multiply these two objects, and you'll see, if you know how to do matrix multiplication, if not, check out my earlier video on it, you'll see that you immediately get the vector 3 minus 1. Pretty cool, right? And it is also only possible with matrices. So you already have one reason why you need matrices. So now let's try and write down the function as we did in the upper example. So let's write down the general function more formally. So our function f goes from R2, our domain, to our codomain, R2. It takes a random vector xy and it maps it to our new vector, which is now 1, 0, 0, minus 1, x, y. So now you see that applying a matrix to a vector can be seen as a map. And this is one of the main reasons why we need these matrices. Now you might say, well, okay, but couldn't I have written down this map also as, for example, x minus y? Because if you do this matrix multiplication, you would get exactly this. And then you would say, well, I don't need this matrix in front of my vector. And that's true. But if it's possible, and it is not always possible, but if it is possible, and it is basically possible if it is a linear map, and we're going to look more into this in a later video. But if it is possible, you want your coefficient matrix to be separate, because from this matrix alone, you can read or find out a lot of information about the map. And these are information about the kernel, about the image. Probably you don't know what these things are now, but later you're gonna think, ah, yeah, exactly, that's why we need these matrices. All right, so now you saw that in order to mirror your vector, you need a matrix. Now up here, we stretched our vector. But now let's try and rewrite this thing differently, because it's not so nice to just, it's nice, but we can also write it as follows. So lambda times xy is exactly the same as lambda times 1, 0, 0, 1 times the vector xy. So this again is a matrix multiplication. And you see that if you do this matrix multiplication, you would get back exactly the vector xy. So this matrix here, and this matrix is the so-called identity matrix, which we write down like this. Oops, this is not good. Which we write down like this very often. And we write down the dimension of the matrix by a 2 cross 2. And you see that this is basically a 1, and this is the 1 of the matrices. So if you apply a 1, so if you multiply by 1, 5 times 1 gives you 5. 1 doesn't do anything to 5. Same goes for matrices. If you apply an identity matrix to another matrix, which means you matrix multiply the identity with another matrix, this won't do anything to the matrix. So it's as if you multiply by 1. So obviously this is the same as this. So this equal sign is perfectly valid. And the identity map always has 1s in the diagonal and 0 everywhere else. And also it's always a square matrix. All right. So then what we can do is we can multiply the lambda with the matrix. it's basically a scalar matrix multiplication. So what we do is we multiply each entry in the matrix by this scalar. Then we have 1 times lambda, which gives you lambda, 0, 0, lambda, times xy. And now you see that you can write down this multiplication of a vector with a scalar also as a matrix multiplication of this matrix with a vector. So stretching and shrinking can also be described by matrices. So in fact, you can describe shrinking and stretching by matrices. You can describe mirroring. You can also describe rotations. I'm going to treat this in a separate video, so you can rotate your vector about a certain angle, and there's this called rotation matrix in all different dimensions, and this rotates your vector about a certain angle. So you see that these maps with matrices are geometrical maps from one coordinate space to another coordinate space. Now, the final thing that I want to tell you, and basically the aim of this video, is that you are not afraid anymore of such functions. So functions which go from some random coordinate space to a new random coordinate space. Up here in my examples, we always had the R2 which goes to the R2, so we had not different vector spaces or coordinate spaces of different dimension, but in general this could be a map from R2 to R3 and so on. Then you wouldn't have a square matrix, but in order to get an R3 vector here, so if we would change this to an R3, you would need a different shape of your matrix. You would have a this would be an object of R, 2 rows, 1 column, 2 cross 1, and then you multiply this 2 cross 1 object on an R3 cross 2 object in order to get an element in here. So the matrix wouldn't be a square matrix anymore. That's what I wanted to say. And otherwise, if it would be a map from R3 to R3, you would have a 3-dimensional, or not a 3-dimensional, but a 3 cross 3 matrix. All right. So now, in general, we have this, and you have some argument, which is the vector x, and this is an element in Rn. So this vector has n rows, and this gets mapped to some general matrix A, and now the dimensions are m cross n times your vector x. And the dimensions of the matrix are like this because the vector is an n cross 1 object, since it is in the Rn, right? You can view vectors also as matrices. So this, for example, 1, 2 is, for example, an element of R2 cross 1. All right? If you don't understand this, go check out my earlier videos on, I think, what is a matrix. Then, what did I want to say? So, and then from this, you know that the n has to go away because this is the dimension which has to be the same. And then we are left with an m and a 1, and therefore your resulting vector, let's call it y, would simply be an element of R m cross 1, which we can abbreviate by Rm. I hope you understand. So now you see how we can use a matrix, in this case this A, and am cross n is obviously an element of R m cross n, and it could have been also an element of C of the complex vector space with this dimension, but we just focused on the real vector spaces. And so you see now how you can use these matrices to describe maps from one coordinate space to another coordinate space. Thanks for watching. Rate the video, give me a thumbs up if you liked it, and I hope you subscribe to my channel, and see you soon again on Lucky Math.